Each electronic component undergoes strict inspection, verifying electrical performance, dimensional accuracy, and reliability before entering assembly. Laser inspection scanning microchips, futuristic precision, trust engineering moment. Printed circuit board manufacturing forms the foundation of inverter architecture, creating pathways that control power flow across the entire system. PCB layers appearing stacked, glowing traces forming, visual intelligence reveal moment. Automated placement machines position hundreds of electronic components onto circuit boards with microscopic accuracy, enabling high-relay control systems. High-speed pick-and-place heads moving rapidly, hypnotic precision electronics choreography moment. Solder paste application prepares connection points, allowing components to be permanently bonded during controlled heating stages. Solder paste printing smooth spread across PCB, satisfying surface detail retention moment. Reflow ovens heat circuit boards, precisely melting solder to create stable electrical connections across complex inverter circuitry. Boards traveling through glowing thermal tunnel electronics transformation moment. Optical inspection systems scan every board, detecting microscopic defects and ensuring electrical integrity before module integration begins. Approved circuit boards move into power module assembly, where high-power semiconductor devices are integrated to handle motor control loads. Large power semiconductor placement scales electronics to power. Power semiconductors such as IGBTs or MOSFETs switch electricity at high speeds, precisely controlling how energy flows from battery to motor. Thermal interface materials are applied between power devices and cooling plates, ensuring efficient heat transfer during operation. Cooling plates are installed to dissipate heat generated during rapid switching, enabling sustained high-performance inverter operation. Cooling plate alignment, metallic surfaces reflecting precision engineering in the moment. Protective housings enclose inverter modules, shielding sensitive electronics from vibration, moisture, and environmental stress. Housing closing sequence electronics disappearing into protected enclosure, trust reliability moment. High-voltage connectors are integrated, allowing the inverter to interface directly with battery systems, motors, and vehicle control architecture. Fully assembled inverter units move to calibration stations, where control parameters are programmed and initial functionality is verified. Calibration screen activating, inverter test rig connects waiting. Software configuration defines switching behavior, power delivery efficiency strategies, and safety limits across operating conditions. Software tuning interface adjusting performance curves, precision intelligence moment. Functional testing simulates real vehicle loads, verifying stable operation across voltage ranges, temperature conditions, and dynamic demand. Inverter powering motor test rig, real energy flow validation moment. Thermal validation confirms cooling performance, ensuring the inverter maintains efficiency and reliability during sustained high-power operation. Thermal imaging revealing heat distribution engineering, trust cinematic moment. Mechanical durability testing exposes inverter units to vibration and stress, replicating real-world driving environments before approval. Inverter vibrating on test platform, rugged reliability proof moment. Final inspection verifies assembly accuracy, electrical integrity, and software configuration, ensuring every inverter meets strict performance standards. Inspection camera scanning inverter, rotating quality of confidence moment. Approved units enter automated packaging lines, where protective materials secure sensitive electronics for transportation and integration. Logistics systems coordinate delivery to vehicle assembly plants, synchronizing inverter supply with battery and motor production schedules. During vehicle assembly, the inverter is installed alongside battery and motor, completing the core electric powertrain control architecture. Inverter placed into EV chassis, iconic integration brain placement moment. Electrical connections link inverter, battery, and motor, enabling precise control of torque, speed, efficiency, and regenerative braking behavior. Once integrated, the inverter continuously regulates power delivery, converting DC energy into dynamic AC signals that control motor behavior in real time. Inverters also enable regenerative braking, allowing vehicles to recover energy and return it back to the battery during deceleration. Continuous software optimization improves inverter efficiency, reducing energy loss and extending overall electric vehicle driving range. Efficiency metrics rising, digital performance clarity moment. Engineers refine semiconductor design, switching speed and cooling architecture to handle increasing power demands across modern vehicles. Manufacturing scalability allows inverter production to grow alongside global electric vehicle demand, reducing cost and accelerating adoption. Research laboratories explore next-generation inverter architectures, focusing on higher efficiency, reduced size, and improved thermal performance. Experimental inverter prototype glowing under lab lighting and prototype rotation dissolved at thermal simulation visualization. New semiconductor materials such as silicon carbide enable faster switching, reduced losses, and higher power density in modern inverter designs. Improved cooling strategies allow compact inverter designs to manage higher power loads, supporting next-generation electric vehicle performance. Cooling flow visualization inside compact inverter. Inverter manufacturing plays a critical role in the electrification movement, enabling precise control of power across modern transportation systems. From production to infrastructure, this cinematic transformation reveals the power of innovation. Advanced control software continuously adjusts inverter behavior, optimizing torque response, efficiency, and driving smoothness in real time. Integration between inverter battery and motor creates a synchronized powertrain ecosystem, delivering seamless electric vehicle performance. Engineers continue refining inverter hardware and software to support faster charging, higher efficiency, and expanded vehicle capability. Is progressing, a cinematic insight moment into this generational comparison. Future inverter designs aim to become smaller, lighter, and more powerful, supporting compact, high-performance electric vehicle platforms. Inverter efficiency directly affects electric vehicle range, making precise power control essential for maximizing real-world performance. This efficiency comparison visualization provides a metric connecting design to high-speed production. High-volume inverter manufacturing reduces cost, enabling electric vehicles to become more accessible as production scales globally. Global supply chains deliver semiconductors, electronic components, and cooling systems, ensuring continuous inverter manufacturing operations. Quality control systems verify every inverter meets strict electrical safety performance and durability standards before deployment. Inverters enable smooth acceleration, efficient energy use, and regenerative braking, defining the intelligence behind electric driving experience. Battery, inverter, and motor together form the core electric powertrain, transforming stored energy into controlled motion across every driving condition. Continuous inverter innovation improves efficiency, reliability, and performance, accelerating the evolution of electric transportation systems worldwide. EV inverters represent the intelligence behind electric mobility, precisely controlling energy flow and enabling the seamless driving experience defining modern electric vehicles.